So with question 2, we're on to acids and bases, and what you have to remember about acids is that they're compounds which release protons, which are H+ ions in solution. So you can figure out the answer to the first bit by just remembering that if you've got a compound H2SO4, when it dissolves in water, those hydrogens can leave and form H+ ions. So the obvious answer to the question is that you can get H+ ions, and what that leaves behind are sulfate ions, SO4 2-. You could also, if you wanted, consider the possibility that just one of the hydrogens might leave as H+, which would give you the third possibility, HSO4-, and that would be fine as well, but the most obvious answer is those two. And remember, you can do that with any acid. Hydrogens leave in the form of H+, and the rest of the molecule is left behind as a negative ion. Okay, so now we've got this reaction of a carbonate with an acid, and we've got 3 marks up for grabs to describe what you would see and then to write the equation for this reaction. The word see there is in bold to emphasise the fact that it's looking literally for what you can see with your eyes. So any comments about what the ions are doing or the molecules are doing, you're not going to get marks for because you can't see that. It's literally what you can see on the bucket scale when you do the reaction. So let's write down the equation first, because the equation tells you, actually, at least if you put the state symbols in, what's going on. It doesn't ask for state symbols here, it doesn't matter if you haven't put them in, but they're useful just to tell you what goes on in the reaction. So we've got potassium carbonate, and they've kindly given us the formula for that, and it says solid, so that's okay. And we're adding dilute sulfuric acid, and again we've got the formula for that. So they're being kind in this question, and with both of these, that those are formulae that you might well be asked to make up for yourself. So don't just assume because they've been nice to you here that that will always be the case. So, general recipe. Acid plus carbonate goes to salt plus water plus carbon dioxide. You must learn those essential acid-base reactions. So, acid plus carbonate goes to salt plus water plus CO2. And the salt will be potassium sulfate, because you've got the potassium ions from there, the sulfate ions from the sulfuric acid. Be very careful before you write down the formula of potassium sulfate to think about the charges on the ions. That's always the tricky bit with salts, that you mustn't just write down the first thing that comes into your head. So stop and think for a minute that we've got potassium ions at K+. You know that because potassium's in group 1, so it will only form 1+ ions. Sulfate, on the other hand, is 2-. And ideally that's a formula you've learned. Remember, sulfate, carbonate, nitrate, those ions you should really memorise. But if you haven't remembered them, you can also figure it out from there. Because you've got 2 H+ leaving, 2 pluses must be balanced by the 2 minuses on the sulfate. So 2-. And that therefore means that you've got a mismatch there, and you need 2 potassium ions to balance the sulfate, so it's K2SO4. And salts, generally speaking, are soluble. I mean, there are plenty of exceptions to that, but you assume that the salt will be soluble, and that's going to be important for the observation. So whenever you do these acid-base reactions, unless you're given information to the contrary, assume that the salts are formed in solution. And the other products, as we've said, are liquid water and carbon dioxide gas. So you have a quick look at that and say, does it balance? And astonishingly, yes it does. You don't need to do anything else to it. So that's your equation. So make sure you've got that. As I say, if you haven't got state symbols, it doesn't matter, but you need to have got all the formulae right, and that's the one to be careful of. So observations, well, the state symbols tell you, first of all, you've got a solid compound at the beginning, but if you look at the products, there's no solid anymore. So the first observation is that the solid dissolves in the acid. The second observation arises from the fact that you've got carbon dioxide being formed. So what you say is that you get bubbles of gas, or effervescence, or fizzing, any of those words to describe the fact that the gas is produced. But remember, it's what you see that you have to write down, so bubbling, or words to that effect is what you need to say. Okay, that's fine for 3 marks. The other part of the question then is a calculation, and it's based around a titration experiment. It's important with questions like this to make sure that you've got clear from the description what's going on in the experiment. And you may find that it's worth almost like drawing a little sketch or something to take you through the steps to make sure that you've got the method clear. So let's have a look at that here. It says, first of all, that he took 2 grams of this caustic soda material and dissolved it in 250 cm cubed, or to make a solution with a volume of 250 cm cubed. So in the starting point we've got a flask or whatever with 250 cm cubed, volume of solution formed from your 2.0 grams of solid going into there. And then from that you just take 25 cm cubed and put that in a different flask. Okay, so smaller volume now, and react that with sulfuric acid. And you can imagine doing that as a titration, so you have a burette up here and the sulfuric acid goes in like that, and that's 0.100 mole per dm cubed sulfuric acid. Okay, and that's the sodium hydroxide in the flask. So that's the basic setup, that we start with 2 grams of impure sodium hydroxide, in it goes into 250 cm cubed, and then from that stock solution we take just 1/10 of it, 25 cm cubed, and react that with just enough sulfuric acid to neutralise it, and that's what you measure in the titration. So we need to keep that setup in mind as we go through the calculation to make sure that when we ultimately calculate the percentage purity, we take all those steps into account. But it leads us through it, at least for the first part. So first it just wants the moles of sulfuric acid, and when we're working with substances in solution like this, the formula that should leap straight away into your mind as soon as you realise it's solution chemistry is moles is equal to concentration times volume in dm cubed. Okay, so we should have that information there, and indeed we have, because it tells us that we had 24.60 cm cubed of sulfuric acid is the volume, but remember that has to be divided by 1000 to put it in dm cubed. So it's really important to remember this formula not just as concentration times volume, but as volume in dm cubed, so you remember that divide by 1000 step. And the concentration, it tells us, is 0.100 moles per dm cubed, and that comes to 0.00246 moles. Okay, that's part 1. Part 2 says, well, okay, so how much sodium hydroxide was there? And that's where the equation comes in. So if you look at the equation, it's there on the sheet, and it tells you that every mole of sulfuric acid reacts with 2 moles of NaOH. That's what the 2 in the equation is there to tell you. In other words, however many moles of sulfuric acid you've got, which is that much, you have to double it to find the moles of NaOH. So really important to practice using equations in that way. To read that equation as meaning the moles of sodium hydroxide will be twice as many as the moles of sulfuric acid. So we can get moles of NaOH is 2 times the moles of sulfuric acid, and we can just double that number and get 0.00492 moles. And that's the answer to part 2. Okay, so those are both fairly straightforward. Now 3 is much trickier because it doesn't give you nearly so much help. So now this is really where it tests, do you understand the experiment? So you've got to think, well, what do we know? We know the moles of sodium hydroxide, and that's the moles of sodium hydroxide here, okay, in this flask, because we calculated how many moles of sulfuric acid went in to react with it. So what we've calculated just by doubling it is how many moles of sodium hydroxide there were in the actual reaction. So the first thing we have to remember now is that that 25 cm cubed came out of a total of 250 cm cubed. So the first thing we have to do now is to realise that we've got to multiply that number by 10 to get the total moles of sodium hydroxide in our original solution. And that's a very common thing in these titration calculations. So if you just think that you tend to take a small volume out of a bigger volume, and most often, not always, but most often you're just taking 1/10 of it. So you've just got to multiply by a factor of 10 to find the total. Okay, so if we just carry on with that now, so this is the first part of part 3, we can get that the total NaOH in 250 cm cubed is equal to 10 times the moles of NaOH in 25 cm cubed, which is 10 times 0.00492, which is 0.0492 moles. Okay, so that's now the number of moles of sodium hydroxide that there were in this pot. We can then convert that into a mass, because we know what the MR of sodium hydroxide is, or we can figure it out. So we can get that the total mass of NaOH in 250 cm cubed is moles times MR, which is equal to 0.0492 times, well, the MR 23.0 for sodium, 16.0 for oxygen and 1.0 for hydrogen adds up to 40.0, and that comes to 1.968 grams. Okay, so that's the actual moles, that's the actual mass of sodium hydroxide that was dissolved in here. But remember that the mass of the impure material that went in there was slightly more than that, because you've got the mass of the impurities as well. So 2 grams went in, but only 1.968 out of that was the pure sodium hydroxide. So to get the percentage purity, we just take that mass of sodium hydroxide as a percentage of the total. So the percentage purity, and it's worth learning this as a sort of general recipe if this doesn't seem kind of immediately obvious to you, and it's one of those things that for some people it seems like common sense, but if it doesn't, that's fine. You can just learn the recipe. That the percentage purity is, if you like, the mass of the good stuff divided by the total mass times 100. Okay, that's what we mean by percentage purity by mass, which is 1.968, we just worked out, was the mass of sodium hydroxide, divided by 2.00 times 100, which is 98.4%. Okay, so percentage purity is worth making sure you understand that, because it comes up in this kind of question, also comes up in relation to ores and things, which again are quite popular in exam questions. And obviously you can do a bit of quality control there. If it comes out at 117%, you know you've done something wrong. But there we are, that's the end of the question.